Good afternoon to everyone. I'm glad to see so many of you here today. Today we're hosting a seminar by Nirvana Caballero, who's a postdoc at the University of Geneva. So let me just give a very brief introduction before she starts. So Nirvana got her PhD in theoretical and computational physics from the National University of Cordoba in Argentina. And since 2018, as I said, she's a postdoc at the University of Geneva, and maybe interestingly enough for this audience, she works in the Department of Quantum Matter Physics, which is maybe not so usual for our speakers, where together with research, she also teaches phase transitions. So Nirvana is an expert of disordered systems, and as probably you may have heard this year through the Nobel Prizes, this is a very prolific branch of physics that has many interesting interdisciplinary applications. And today, Nirvana will show us how exactly these kind of skills acquired from the topic of disordered systems can be transferred to the study of biological systems. So Nirvana, the stage is yours.
Thank you. Thank you very much for the kind introduction. And thank you very much for the invitation. I'm very happy to be here and to have the opportunity to discuss with you about my work. I was telling some minutes ago that I think this is a very, very nice initiative. I saw that you have a very diverse audience and also a very diverse speakers, and you cover many subjects. So I think it's very, very interesting, and I'm very happy to see that you are pushing this forward. As Luca was saying, I'm a theoretical physicist, and I'm interested in the statistical mechanics of disordered systems in equilibrium and out of equilibrium. And I have the pleasure of collaborating with many talented experimental colleagues. And that collaboration allows me to apply the tools of disordered elastic systems to understand very complex systems. And in particular, I will discuss with you today about how are we using these tools to study collective cell migration. And I'm a theoretical physicist, so I see everything through with a physicist eye. So I can, as physicists, we find emergent structures in diverse systems that range from nanometers to kilometers, independently of the microscopical details of the system. And between these emergent structures, we can find one very interesting object, which are called interfaces. And interfaces are defined as a region where a system changes from one homogeneous state to a different homogeneous state. And studying these objects is important because we can extract information about the whole system by just observing a very small part of it. So this is a growing colony of cells. This is a two-dimensional tissue moving over a substrate. And we can define the interface as the edges of the colony. And here is where the tools of the statistical mechanics come into the stage. If I can change my slide, I don't know what's happening. Yes. So one of the most powerful tools to study interfaces is the framework of disordered elastic systems. This is a very powerful framework, and it's a brutal simplification of the system. So to use this framework, one has to define an interface, a function describing the position of the interface as a function of space and time. Of course, this framework is not only restricted to study the edges of a colony, it can also be applied to study other systems. I will mention two examples in which I worked with. One is in the center of the screen is a ferromagnetic thin film. In black, the magnetization of this thin film is pointing outside the screen, and in gray is pointing inside the screen. We can define the interface as a region of the system where the magnetization changes smoothly from one preferential direction to the other. And the same kind of objects, these interfaces, can be observed also in ferroelectric thin films, where instead of having a magnetization with a preferential orientation, we have a polarization which has a preferential orientation. So as I was saying, to use this framework, we have to define a function that defines the position of the interface. And this is a brutal simplification because we ignore all the internal degrees of freedom that the interface can have. But usually this is not a very bad simplification because the width of the interface is orders of magnitude smaller than the total length of the interface. And we have to assume that this interface is smooth and univalued. And you can say, okay, this is a very, very simplistic approximation of the system. Yes, it is. But at the same time, it allows us to do very precise analytical calculations, as I will describe later. So one of the simplest equations that we have to describe how these objects will behave is the so-called Quenchet-Edward-Wilkinson equation. So according to this equation, the dynamics of these objects will be the result of the competition of only a few terms. The elasticity that will try to flatten the interface, it will try to make this interface flat. Some pinning force that take into account disorder present in the system, some external force that can be applied to the system, and thermal fluctuations. And already with this very, very simple equation, we find very rich phenomena. And in particular, we find that the static and the dynamical properties of an interface are intrinsically related. And how can we measure the static properties, the geometrical properties of these objects? We can do that by measuring the roughness. The roughness is nothing more than the correlation of the quadratic displacements of this function describing the position of the interface. And the advantage of this framework is that we can really compute analytically how the roughness of an interface will behave as a function of time. So here I show an equation that can seem very complicated, but in the end is very simple. So this is describing how the roughness of an interface will behave as a function of time for an interface that was initially flat. So these are numerical simulations solving the Quenchet-Edward-Wilkinson equation, where we just consider elasticity and temperature. So when we start with a flat initial condition, as time passes, the thermal fluctuations competing with elasticity will tend to rough the interface. So this interface will become rougher and rougher as time passes. So different lines are different evolution times of the interface. And when we compute the roughness, which is in this plot, in dashed lines, I'm showing the analytical prediction that we have, and in continuous lines is the computation of the roughness for these numerically generated interfaces. And we see a very good agreement. But what is the message that I'm trying to show here is that when the time passes, this roughness will follow a power law, a very well-defined power law that depends on the temperature of the system and on the elasticity C describing this interface. But also, it shows us the initial state of the interface. Since if we have a completely flat interface, this roughness function will be an horizontal line. And that is reflected in the roughness for different times. So we see that there is this flat part of the roughness, and this information is lost as time passes, and the interface becomes rougher and rougher, and the roughness follows a power law. Okay. For the moment, I just described how an interface will behave in this framework, which is the framework of disordered elastic systems. So you have this, you just describe the position of the interface, and you have equations for the position of the interface. There is another kind of approach, which is based on a Ginzburg-Landau model. So instead of just describing the position of the interface, you describe the state of the system. So here I'm showing examples of a one-dimensional interface, and here I'm showing an example of a Ginzburg-Landau model in 2 dimensions. The Ginzburg-Landau model is for an order parameter phi that represents the state of the system. But this is valid in many dimensions, as many dimensions as you want. For the applications that I will discuss later, here I'm showing an example of a one-dimensional interface and of a 2-dimensional order parameter. So in the case of the Ginzburg-Landau model, we describe the state of the system through an order parameter phi, and we consider a few terms. This is the Hamiltonian, this is the simplest Hamiltonian that we can consider, has some term considering exchange between the particles of the system, a double well potential B that mimics the existence of 2 preferential values for the order parameter, an external force that can be applied, and that's it. So it's a very simple Hamiltonian that allows us to describe the state of a system with 2 preferential values. And for the moment, let's consider a non-conserved order parameter. So the simplest equation that describes the evolution of this order parameter will be a Langevin equation of this type, where in this term zeta, we take into account the thermal fluctuations. And when we solve that equation, we arrive to this expression. And why I'm mentioning this? For the moment, it will seem very abstract, but I will try to convince you later about why this is important. So with this kind of approach, we can describe other kinds of interfaces that cannot be described with the framework of disorder elastic systems, with the Quenche-Edward-Wilkinson equation, because in that case, we have to consider univalued interfaces. But with this Ginzburg-Landau approach, this is a simulation of a Ginzburg-Landau approach where the disorder is very strong. And we can see these kind of interfaces, which has a few features of real interfaces. Let's go back to the simple case where we don't have temperature and we don't have disorder. We can compute analytically the solution of the order parameter. We will have as a solution of this equation and a solid tonic profile. For the moment, it's not very important, but the thing is that this can be solved analytically when we try to minimize the Hamiltonian with respect to the order parameter, and we have an analytical expression for that. One way of putting disorder in this Ginzburg-Landau model is putting fluctuations in the height of the double well potential. So these are fluctuations in the height of the energy barrier that the order parameter should overcome in order to go from one preferential minima to the other preferential minima. So for the moment, I described continuous equations, but this can be discretized as any equation. And one way of putting disorder is, for example, the simplest way is to put random number with a uniform or Gaussian distribution from side to side when one does the discretization of the system. And I promise that I will go to the point soon. I'm just trying to show here that with this Ginzburg-Landau model, one can describe interfaces as one does with the framework of disorder elastic system. So one takes the equation of the Ginzburg-Landau that I just showed at the beginning with the disorder put in this way, as fluctuations in the energy barrier that the order parameter should overcome in order to go from one minima to the other. And one can use as an ansatz to do a dimensional reduction of this equation, this solid tonic profile. This solid tonic profile is the solution of the equilibrium case. And there are many terms here. One can play a little bit with the equations. One ends up with an equation like this, it doesn't tell us much for the moment. But the thing is that what we did is that we found a method to reduce the Ginzburg-Landau description to the description of an interface. That means that after we inject the ansatz that minimize the equation in the equilibrium case, we can localize the equation around the position of the interface. For that, we multiply by the derivative of the solid tonic solution. And then we integrate over x, over one of the directions. And okay, maybe the details of the procedure about how do we do that, it's not very important. But what is important, and the message that I'm trying to transmit, is that one can start from a Ginzburg-Landau description here. And with this very simple method that I just described, one can do a dimensional reduction and end up with an equation for the interface. What does it mean? It means that one can have a description in the Ginzburg-Landau state, in the Ginzburg-Landau model, but under some approximation, you don't really need to describe the whole system and the whole state of the system. If you just look at the interface in this Ginzburg-Landau model, it will give you the same information. So that's the take-home message, that this interface approach can seem very simplistic, but it takes into account many things of the system, of the complete system that we have. And that's why I thought that it was very important for me to show this connection between both models, because I can understand that if I tell you, okay, look at the correlations of an interface, and they will tell you a lot of information, probably it's very difficult to see that. By showing this connection between these two models, I'm trying to show you that actually you can extract a lot of information. A lot of information of the whole system is encoded on what's happening on the interface of the system. With this method of connecting these two model systems, one finds that the elasticity of the interface has an expression that depends on the parameters of describing the Hamiltonian of the Ginzburg-Landau model, but one can also compute analytically the elasticity of an interface in a Ginzburg-Landau model, and in both methods we get the same elasticity for the interface. This is another way of checking that the connection that we did between these two models is working very well. But another way is to actually do the numerical simulations. So this should be a video, but it's not playing. There it is. So actually, we did simulations of a Ginzburg-Landau model, which is this order parameter that goes between the green and the purple colors. And we did simulations of just an interface, which is the black line. So on one hand, we have the simulations of the Ginzburg-Landau model where you don't have to define the position of the interface. The system defines the interface for you. And actually you can find a method to extract the position of the interface. So actually when you do the simulations, you have only the values of the order parameter. You can define a method to extract the position of the interface, and then you can follow this interface, which was starting from a flat initial condition as a function of time. And what we also did is to do the simulations of an equivalent interface in 1D and check what was happening with the geometrical properties of these interfaces. This was just a test, a numerical test, to check that the analytical connection that we did between both models was working okay. And these are the results. This is a extracted interface for the one-dimensional Edward-Wilkinson equation. And these are the results of following an interface in the Ginzburg-Landau model. And we computed the roughness of these interfaces in the equivalent models, and we found an excellent agreement between the simulations and the theory, and between the connection of both systems. Of course, that this connection is valid up to some approximation. So here, instead of following an interface as a function of time, these are interfaces that were followed for the same amount of time, but for different temperatures. And we computed the roughness. And in the case of the one-dimensional line, when we compare with our analytical prediction, which is in dashed lines, we see a very good agreement. In the Ginzburg-Landau model, for low temperatures, the agreement is very good. But then when we start to increase the temperature, what happens is that the fluctuations in the bulk they start to be very high compared to the fluctuations of the interface. So this roughness doesn't have a very good agreement with the analytical prediction, but it's not very different. It seems like there is a prefactor that is only changing, but the shape of the roughness, it's not changing too much. And here is, again, just to show, to emphasize how the connection is very good when we consider disorder. In these continuous lines, I'm showing numerical simulations of an Edward Wilkinson equation in one dimension, and in continuous lines, I'm showing the results of the roughness of interfaces in the Ginzburg-Landau model, and we see an excellent agreement. Why I showed you this, and this is a key for what's coming later. So here I show now 2 examples of roughness of different systems that evolved for different times. In these continuous lines, I show a system where we only consider elasticity and temperature. And in continuous lines, I'm showing the roughness of interfaces of a system which has elasticity, temperature, and disorder. So one has 2 terms in the equation, and the other has 3 terms on the equation. And of course, both systems started from a flat initial condition. What we can see is that in both cases, we have the signatures of the flat initial condition of the interface. So the roughness is flat at very large distances. At short distances, all of them have a power law function with the very well-defined exponent, which is 1/2. And also the prefactor depends on the elasticity of the interface and on the temperature. But now we have a second power law, which is due to disorder. This power law has another power law exponent. And we recently found that there is also a third power law, which is the result of the competition between thermal fluctuations and the disorder that gives a power law exponent of 0.9. And the region where you can see this power law on the roughness depend on the microscopical details of your system, on the disorder correlation length, on the elasticity of your interface, on the temperature, and these kind of factors, of microscopical factors. And for the moment, you would say, okay, you showed me many interfaces and roughness and how to characterize the geometry of these interfaces. And here is when the interesting part comes into my presentation. Why I show you why I did this very long introduction is because I was trying to convince you that the roughness has signatures of the main mechanisms in charge of controlling the system. So when we have complex systems, I agree with you that cells or any kind of systems have a lot of physical and chemical interactions that act at many scales. But we also know that not all the interactions are really important. So how do we distinguish which are the main interactions that control our system? I think that's the very basic question that we have in physics, and is try to describe which are the important mechanisms that are controlling our system. And I did this very long introduction just to show you that we are convinced that by measuring the roughness, one can extract this information. One can distinguish which are the main mechanisms controlling a system. So that was the philosophy behind our work. So I have these colleagues, the experimental colleagues they did experiments in the University of Zurich, and they studied these huge tissues proliferating over a substrate. And the idea behind was that we defined the position of the interface as the edges of the colony, and we followed how this interface behaves as a function of time. So since we want to discover which are the main interactions controlling our system, the experiments were done under 5 different conditions. One was control condition, and the other were subject to the effects of inhibitors. And each experiment was repeated 3 times, and images of the front were taken every 4 hours for 3 days, and each front has 7 centimeters with a resolution of 0.8 micrometers. What does it mean? It means that my colleagues had a lot of data. They had, when we defined the position of the interface for these very long fronts with this nice resolution of 0.8 micrometers, we had to analyze interfaces which had 2 to the power 16 pixels. That was a lot. And that's when also my expertise was useful. And it's because when we want to characterize the geometry of these interfaces, we have to compute the roughness. And this is a factorial time complexity problem. That means that we had to do a lot of calculations. And for that, what I did is that I implemented a high performance computational code to compute the roughness by using CUDA that runs on GPUs, on graphical processing units. And with that, you can accelerate the computations by 100 of times. This is also useful, and this kind of acceleration of the computations is also useful to solve the numerical equations that allowed me to connect the Ginzburg-Landau model with the interface model, because there the computations are very heavy. If you would like to do it with normal techniques, it will take an incredible amount of time, and you won't be able to really seriously compute things. So we computed the roughness of these interfaces in these nice experiments. And this is how the roughness of these evolving proliferated cells looks like. So the interfaces were taken every 4 hours, and for each of these fronts, we computed the roughness. And this is how the roughness looks like. And when I saw this, I was amazed, because it's really similar to the roughness that we are used to analyze for these very simplistic objects, which are these one-dimensional Quentia-Dedwall-Wilkinson interfaces. And in particular, what is very easy to see here is that the roughness follows a very well-defined power law for short distances. And these distances are of the typical cell size. But also, in these experiments, my colleagues started from a flat initial condition. I'm a theoretician. I cannot give you many details of the experiments, but what they did is that they put an insert on a Petri dish, and then they removed this insert. So they ensured that the initial condition of the interface was as flat as possible. And that's something that we can see at long distances here. This flat part of the roughness is actually reflecting the flat initial condition of the front. But okay, how can we really extract, besides of me telling, okay, here is a power law and here is an horizontal part, let's do something more serious. How can we do something more serious? Okay, we have to identify power law scaling regimes. And for that, we proposed a method where we fix an initial point to do a fit with a power law. And we fix a window size of equivalent spacing in logarithmic scale. And we compute the goodness of the fit through R squared. So we check how good is to fit these roughness functions of the cell fronts with the power law. And we measure how good is the fit through this R squared value. And this is how the plot looks like. So in this axis, I'm changing the initial point to do the fit. And in this axis, I'm changing the width of the window that I used to do the fit. And the different colors indicate how good the fit is. So if R squared is closer to 1, then the fit is very good. And what we can see is that there are at least 3 maxima on this goodness of the fit. One is at very large distances, which is the reflecting that the interfaces were initially flat. So this is a signature of the flat initial condition. Here, we also see that at short scales, we can fit very well our roughness with a power law. But interestingly, we found also power law at intermediate scales, which are at 4 cell distances and expand for around 5 cells. So this is how the roughness of our cell fronts under control conditions look like. And this is how the roughness of an elastic line in the Quench-Edwards-Wilkinson equation looks like. And we did the same analysis for the elastic line for the Quench-Edwards-Wilkinson, where we know analytically how the roughness will behave when we start from a flat initial condition. And here we see this maxima on R squared, indicating that at these distances, we can fit the roughness very well with a power law. Then there is also a maxima on the goodness of the fit at short scales, indicating that we can fit the roughness with a power law. And there is nothing in the middle. However, on the cells, we see these 3 peaks, indicating that there is something more compared to the elastic line. So we have a short scale power law, a second power law at intermediate scales, and then the third, I say power law, but it's an horizontal line. It's a power law with an exponent 0, which reflects the flat initial condition. So as I said, my colleagues did these very nice experiments, not only under control conditions, but they put different rocks on the cell fronts, on the tissues. And we analyzed how the interface behaves for under the effects of different rocks. So they used colchicine that targets cell division rates. They used cytochalasin B that inhibits cell motility and transmission of mechanical forces. They also use meclofenamic acid that has the effect of disrupting electrochemical signal transmission, and forskolin that does many things to the cells, and it globally affects the cell metabolism. And we can see already by eye that here different scales of green indicate different times at which the images of the fronts were taken. And already by eye, we can see that there is a huge difference in the roughness, visually, in the roughness of these different fronts that evolve under the effects of different rocks. But actually, we can actually quantify that. In particular, we measured the velocity of these fronts, and we found these nice results. So in green, I show you the average colony depth as a function of time under control conditions. And then different colors indicate the average colony depth for fronts under the effects of different drugs. And what we see is that compared to control conditions, the fronts, the interfaces that evolve under the effects of cytocalysin B and colchicine decrease the front velocity. Okay, this is not very surprising because in the case of colchicine, it targets cell division rate. So if you lower the rate at which cells can divide, is okay, quite intuitive that the fronts will move slower. But what was surprising for us is that these other drugs increase the front velocity. In the case of meclofenamic acid, disrupting the communication between cells has the effect of increasing the front velocity, which was a surprise for us. We can also compare the roughness of these different fronts under different drugs. And we followed how the roughness evolved as a function of time. So the initial observation is after the 4 hours and is here represented in continuous lines for the control conditions, which is the green front, the green line. And with 2 inhibitors, I chose cytocalysin B and meclofenamic acid, but we analyzed all of them. And what we see is that there is a strong evolution of the roughness as a function of time, as shown in dashed lines. And what we did is that we analyzed what's happening in these regions that we identified with the method that I showed you before. In particular, we found that we have this horizontal part of the roughness that is reflecting the flat initial condition of the front, but we also found 2 power laws describing the roughness. And this is also the prefactor of the this is the evolution of the prefactor as a function of time. And we see that there is a clear difference between the front under control conditions and with different drugs. But in particular, what we found importantly is that there are these 2 power laws, and these 2 power laws have very different power law exponents. This is 0.6, and this is around 0.3. So for the moment, we don't have an explanation for that, but we wanted to go further and try to understand what this power law means. So what we did is that we used this Vertex model. This is typically used to model cells in tissues. And it's a very simplistic model because you represent each cell by an hexagon. And you consider, we use this Hamiltonian, is based on energy minimization. We consider that each cell has an elasticity, a preferred area, a preferred perimeter, and we also consider line tension along cell-cell junctions. And we can try to simulate what's happening with this experimental protocol of starting with these simulations of the Vertex model from a flat initial condition and let the system evolve. And what we do is that we allow, we can compare our simulations. We can introduce the division rate of the cells by comparing with the observation in the experiments. We also have access to, for example, to the preferred area of each cell, so we can introduce parameters of the experiments to do this modelization. We followed the interfaces as a function of time for these systems, and we computed the roughness for this Vertex model. And we were trying to see what was happening at intermediate scales. And under any circumstances, we tried all the possible parameters. We found this power law exponent that we observe on the experiment, which gives 0.3. So under no conditions we could reproduce with these numerical results this power law that appears on the roughness. That means that there are many possibilities we are working on right now directly, and is that the vertex model is not enough because we only consider interactions with nearest neighbors. And what the roughness in the experiment is telling us is that there are some intermediate scales interactions that are important in the system. In the vertex models are not taking into account. That's a possibility to introduce this kind of interactions, mid-scale interactions in the vertex model, or directly use other kind of models. There are now emergent other models in the literature, especially because our computational resources are being enough to do more complicated approaches. And with that, I would like to conclude. I think I'm fine with the time. The main message is that the interface of a system, not only on biological systems, but also in many other systems, we have applied this framework to try to understand other systems, and it was very successful. More successful, I would say, that in the case of the cell fronts, what we thought that we could find some model to try to reproduce experimental results. Because I think when one uses a model to describe an experiment, one needs to identify how good the model is. And I think that this roughness, this observable, gives us that information. We can, through the roughness, identify how good our modelization is. And also then try to understand better what's happening on the experiments. That's why I find very interesting that even targeting different phenomena that were happening in the colony by adding different inhibitors allows us to do a more in-depth analysis of what's going on in the migration of these tissues. So I would say that the message I want to transmit is that the roughness gives us a lot of information about the system, and it also tells us how good our modelization of the system is. And in particular, when we apply this framework to study these particular experiments, we found that to describe collective cell migration, one needs to take into account a hierarchy of interactions, in particular these mid-scale interactions that are not usually taken into account in any modelization. We are working on that direction now. And I think that's the most valuable part of this work. Now it allows us to propose new theoretical models to describe this phenomenon. And with that, I would like to warmly thank my collaborators. It's really a pleasure to work with them. This was a work done in collaboration with very talented experimental colleagues, and I'm grateful for that to them. Thank you very much.